This lesson will discuss aircraft upset conditions, causes, recovery procedures, and best practices. Although loss of control in-flight accidents are relatively rare, they make up an average of 1/4 of all aircraft fatalities worldwide. An ICAO symposium tasked with addressing these incidents showed a lack of proper pilot training industry-wide for aircraft upset awareness and recovery techniques. The committee expressed support for a global and coordinated effort to address loss of control accidents. Individual national aeronautics associations are working with ICAO to develop training for identification of and recovery from upset situations. In the U.S., this has led to a revision of the Code of Federal Regulations. Part 121-419A-2, Subparts 11 and 12, now stipulates the requirement for pilots to receive instruction in the following relevant areas: stall prevention and recovery in clean configuration, takeoff and maneuvering configuration, and landing configuration, and upset prevention and recovery. Further along in Part 121-419, it is stated that the training will be required no later than March 12, 2019, and must include 2 hours of ground training. Upset recovery training programs are designed to include both academic elements as well as maneuvers in a flight simulator training device, or FSTD. This training is required for pilots undergoing initial, transition, and upgrade training. In conjunction with the discovery of a pilot training deficit, it was found that most Level C and D training devices could not accurately replicate aircraft characteristics in upset envelopes. New requirements were put into place for simulator upgrades to include proper aerodynamic handling for these flight regimes. Thanks to industry and manufacturer safety improvements over the past few decades, most pilots will never experience an aircraft upset during their career. Pilots must regularly train for and be vigilant in assessing upset conditions. The goal of this lesson is to instruct flight crews in the following areas: recognition of upset conditions, avoiding upsets, and upset recovery. This lesson is designed to preface and complement the required simulator training specific to upset recovery procedures. For further information on simulator profiles and expected completion standards, consult your training manuals. An airplane upset is defined as an airplane in flight unintentionally exceeding the parameters normally experienced in line operations or training. In other words, the airplane is not doing what it is commanded to do and is approaching unsafe parameters. The key word in defining upsets is that it is unintentional. Although actual values may vary depending on situation or aircraft type, it is generally agreed that any of the following parameters, when achieved unintentionally, describe an upset condition: pitch greater than 25 degrees nose up, pitch greater than 10 degrees nose down, and/or bank angle greater than 45 degrees. An upset can also be defined when the aircraft is within the parameters above, but at airspeeds inappropriate for the conditions. In every possible scenario, avoiding an aircraft upset is far more desirable than having to recover from one. Prevention is key to upset condition training. Active monitoring of the aircraft and proper judgment is critical to avoiding an upset condition. Active monitoring can be defined as a proactive, knowledge-driven process of encountering and keeping track of how things are in relation to the perceiver and his expectations to enable the perceiver to take meaningful action. This means seeking relevant information, making important information available, filtering information that is meaningless, creating new information, and offloading cognitive processing onto the interface or adapting the interface to support monitoring. Proper monitoring includes each pilot doing the following: know and understand the expected airplane state for the situation. Communicate expectations. Keep track of current airplane state. Detect and communicate deviations from expectations. Assess risk and decide on a response. Update and communicate understanding. And take timely corrective actions. These practices are the foundation for preventing and avoiding aircraft upsets through early intervention. Early interventions and correcting undesired flight path discrepancies will stop a divergence before it can evolve into an upset. A significant portion of this lesson will explore the root causes for aircraft upsets. The strategy is that if crews gain an increased awareness of the conditions and causes of upsets, they will be much better equipped to avoid flying into an upset condition. Pilots engaged with the aircraft are much more prepared to intercept an unintentional divergence before it develops into an upset. If the flight crew is able to recognize the conditions for and thereby avoid an upset, then the condition will recover itself. Again, upset avoidance is always the best policy. Although the reasons for aircraft upsets may vary greatly, and in some incidents may be hard to ascertain, it is understood that the main categories of upset causes are: environmentally induced, system anomaly induced, pilot induced, or a combination of any of the above. Environmental factors are the largest factor in airplane upset incidents. With the exception of wake turbulence, environmental factors all derive from weather sources. Weather events that result in airplane upsets can include any of the following: turbulence, clear air turbulence, mountain wave turbulence, wind shear, thunderstorms, microbursts, or icing. Non-clear air turbulence is that which is caused by convective or frontal air disturbances. This type of turbulence is typically associated with areas of measurable precipitation. Under most circumstances, these areas of weather-related turbulence are accurately forecast and can be detected real-time using onboard weather radar. For these reasons, this type of turbulence is the easiest to avoid. Proper flight planning and situational awareness will reduce the number of situations where aircraft are flown into areas of known turbulence. If weather penetration does occur, severe or extreme turbulence can lead to an aircraft upset condition. Clear air turbulence is harder to forecast and therefore harder to avoid compared with convective weather turbulence. Clear air turbulence is most often the result of interference with jet streams. Atmospheric jet streams may exist in any number, at any time, and in any location. This, along with jet streams' characteristic of not having a consistent shape or size, means they are difficult to predict. Knowledge of high-altitude meteorology can aid in jet stream awareness, but the best predictor for clear air turbulence is pilot reports. Mountain wave or orographic turbulence is caused by disruption of wind flow by natural or man-made barriers such as a mountain range. Like clear air turbulence, this type can be formed in areas of no convective weather or precipitation. Because mountain wave turbulence is simply a factor of wind and geography, it can be easy to predict. For example, when transiting the front range of the Rocky Mountains with a strong westerly wind, there will be a very high chance of mountain wave turbulence. While forecasting this kind of turbulence may be easier, avoiding it may not always be feasible if operating into or out of airports near these areas. Wind shear is defined as a change in wind velocity over a short horizontal or vertical distance. This can be caused by a number of different phenomena, some of them more avoidable than others. The best strategy for avoiding wind shear is to monitor pilot reports and be aware when operating in areas with known shear. While there are different types of thunderstorms, all of them can be considered hazardous when it comes to turbulence and aircraft upsets. All thunderstorms are comprised of strong updrafts and downdrafts. Many storms also feature a gust front, an area of very strong winds and turbulence caused by the downdraft of rain-cooled air out of the storm. Microbursts, a phenomenon associated with very powerful storms, are a rapid outflow of air from the base of convective weather. It is thought that about 5% of thunderstorms will produce a microburst. Intentional flight into a thunderstorm or microburst presents a substantial risk and can very easily lead to an aircraft upset. Over the years, there has been a great deal of study to understand the formation of icing and mitigate its impact on safe flight. While the scope of this lesson is not to instruct in the best practices and techniques for operations in icing conditions, it should be stated that icing is a serious hazard that can and has led to aircraft upsets. Even relatively small control surface contamination can result in any of the following: unexpected airplane handling characteristics, degradation of lift capability, increased drag, or possible unanticipated changes in stability and control. Avoiding icing to keep a clean airplane is always the best course of action. If flight into icing conditions is unavoidable, appropriate precautions should be taken. Use of autopilot and autothrottles can mask the effects of airframe icing, so consider using manual controls. All applicable anti-ice systems should be operated when necessary. In addition, when in terminal environment, it is sometimes a good practice to operate at slightly higher than normal airspeeds. For more specific information on operating in icing conditions, consult your operating manuals. Wake turbulence is the leading cause of environmental upsets. Most commonly, a wake turbulence encounter produces an induced roll or pitch maneuver. In very rare instances, wake turbulence can cause structural damage to the aircraft, with some pilots describing the event like hitting a wall. The strength and severity of the wake, as well as the aircraft's capability of escaping the encounter, will vary greatly between instances. In any case, the pilot should be ready to recover from any resulting upset condition. As with any other upset cause, avoidance is the best strategy. Wake turbulence avoidance involves following these guidelines. Be aware of larger aircraft flight paths. Take note of touchdown and takeoff points when following heavy aircraft. Incorporate wind effects when forecasting wake locations. Stay above and upwind of heavy aircraft flight paths when possible. And delay takeoff or landing behind heavy aircraft if safe wake separation is in doubt. If wake turbulence is encountered, keep in mind that with either little or no input, the aircraft will be expelled from the vortex. Therefore, normal roll inputs should be sufficient to oppose the wake roll moment. Do not over-control the aircraft. Let the wake turbulence encounter end, then recover as appropriate. Despite a vast improvement in airplane systems integrity and reliability, failures can and do still occur. The majority of system-induced airplane upsets are survivable as long as the correct actions are taken by the flight crew. Pilot familiarity with aircraft systems and how they can fail will greatly improve situational awareness and help avoid aircraft upsets. While any variety of systems failures can lead to an upset, they are generally divided into one of the following categories: flight instruments, autoflight systems, flight controls, and other anomalies. Flight instruments are an integral tool for safe flight. Because of this, most modern airliners are equipped with multiple redundant systems in the event of a failure. However, because of the increased reliability of these systems, problems with identification can arise when failures do occur. A lapse in cross-checking and failure management can lead to a breakdown in spatial situational awareness, which can then very easily lead to an upset. In one example, an aircraft attempted to take off with the captain's side pitot tube blocked. The crew continued the takeoff, after which there was confusion regarding the airspeed discrepancy between the two pilots' indications. Neither pilot attempted to cross-check with the standby system to clarify which system was correct. As the flight crew maneuvered in an attempt to remedy the increasingly frequent overspeed stall warnings, an upset was entered that lasted for 2 minutes before finally impacting terrain. The autoflight system integrates and manages a large array of flight inputs and controls. Because of the large array of aircraft control managed by the autoflight, as well as the increasing reliability of the system, the pilot community has developed a level of confidence and complacency. A fault or mismanagement in the autoflight system may lead the aircraft into an unusual attitude. If there is any doubt regarding the validity of autopilot inputs or commands, the crew should disengage the autopilot, autothrottles, or both. Be aware that some failures may be gradual and unenunciated, making identification difficult. Care should be taken during disengagement. Unexpected control forces and trim settings may result in an abrupt attitude change and possible aircraft upset. Failures of the flight control system can directly lead to an aircraft upset with no action from the flight crew. Flap or slat asymmetries, spoiler malfunctions, trim runaways, rudder hardovers, and others, can impose an immediate, uncommanded roll, pitch, or yaw input on the aircraft. The best practice for these failures is for pilots to always expect the unexpected and have a predetermined course of action to remedy the condition. This is especially true in low-altitude, low-speed scenarios, such as takeoff and landing. Flight control failures are unique in that they may be the only type of system failure that requires immediate corrective action to prevent or recover from an upset. Other specific system anomalies that can lead to an aircraft upset include, but are not limited to, the following: stall warning failure, engine failure, or cargo shift. In some instances, upsets are caused by the flight crew with no identifiable system failure. These pilot-induced upsets can be triggered by any number of events, but the two most common factors involve misleading sensory inputs and the inability to see the horizon. These two factors lie at the root of pilot-induced upsets, as they take away the pilot's ability to discern a proper flight attitude. Pilot-induced upsets can be onset by some of the following events: misinterpretation of instruments, adjustment of attitude and power, inattention, distraction, vertigo or spatial disorientation, pilot incapacitation, or improper use of automation. Instrument cross-check is an important skill that all pilots learn during initial instrument training. However, the workloads of different flight phases and the ability of different pilots will vary. Some pilots are more experienced or simply more skilled at proper instrument cross-checking. In low workload flight phases, there are relatively few changes in aircraft attitude, so instrument scan is not as demanding. During these times, it is often adequate for a single pilot to monitor the aircraft attitude. High workload phases, however, will demand both pilots to give more attention to the flight instruments. All flight crews should train and practice the skill of proper instrument cross-checking. During flight, it is necessary for the flying pilot to anticipate pitch, roll, and power inputs to meet the desired flight path. This anticipation of flight control inputs and the knowledge of how the inputs will affect the flight path is called airmanship. If the flying pilot is reactionary to the airplane path needs, as is common when new to the aircraft type or experiencing a loss of situational awareness, over or under controlling can occur. This leads to a cycle of unplanned and excessive control inputs that can lead to a divergence from the intended flight regime. In some upset incidents, there have been occasions of two pilots applying opposing inputs in an attempt to anticipate the flight path. Inattention is simply defined as neglecting to monitor the airplane's performance. This can mean the exclusion of attention to any aircraft system or function. Examples of inattention might be forgetting to add thrust when leveling off in an airplane, either without an autothrottle system or one that is inoperative. Small changes in the flight path or attitude may be easily missed when the crew is inattentive. Distraction, like inattention, involves the flight crew not monitoring the flight path or aircraft systems properly. In the case of distraction, however, the root cause is an external or self-induced task that absorbs the attention of the pilots. Distractions can be duty-related, such as running checklists or completing paperwork, or non-duty related, such as eating, drinking, or conversing. In one example, a flight entered an upset after the captain left the flight deck and the first officer began completing paperwork on a clipboard. At some point, the autopilot inadvertently disconnected, and the first officer did not realize until the aircraft was in a steep, nose-down right bank. In this example, both flight crew members were distracted, the captain with non-duty related items, and the first officer with paperwork. Sensory illusions, such as vertigo and spatial disorientation, are caused by a conflict between instrument and visual indications and what the pilot feels is the correct attitude. Although vertigo and spatial disorientation can occur in any weather conditions and at any time, they are most commonly experienced at night and in marginal weather with an undiscernible horizon. This makes anticipating or recognizing spatial disorientation difficult. In fact, in some instances, the pilots may not even be aware of the discrepancy between perception and actual flight path. Unrecognized spatial disorientation is much more common during high task saturation portions of the flight. These distractions, coupled with inadequate instrument scanning and an inability for pilots to overcome the conflict between sensory and visual information, can directly lead to an aircraft upset attitude. In most instances, only one pilot will succumb to spatial disorientation at any given time. Therefore, the best strategy for resolving disorientation is for pilots to monitor each other's control inputs and communicate if something unexpected is happening. Although a very rare event, there are times when a pilot may become physiologically incapacitated. The onset of incapacitation can happen abruptly or slowly and partially with a subtle degradation of mental or physical performance. Of these, the latter is more dangerous because of the lack of clear identifiable signs. This is also the more common type of incapacitation. If not caught, pilot incapacitation can quickly lead to an aircraft upset. Should either pilot suggest a loss of mental or physical capabilities from their crew, they should immediately query them with verbal communication. If there is a lack of response after multiple efforts, the other pilot should immediately assume aircraft control. Advancements in aircraft technology have resulted in higher levels of automation, which, in turn, have resulted in higher levels of complexity. This complexity has led to instances where pilots either mistrust or do not understand autopilot modes and control inputs. Improper mode management of the autopilot can lead to excursions into the high or low speed buffet regime. Manual override of the control wheel during coupled autopilot operations can cause abrupt disconnection and subsequent upsets. The best strategy for avoiding these upsets involves pilot education and training to maintain strict proficiency on the autoflight system and operation. Anticipating autopilot mode changes and operations will increase situational awareness and decrease the chances of an upset. Finally, and most commonly, there are times when a number of factors all contribute to an upset. Frequently, a single event may initiate the onset of other causes, which in turn result in an aircraft unusual attitude. For example, an autoflight system failure may go undetected by the crew due to distraction. When finally noticed, possibly the crew overreacts with pitch, roll, and thrust commands, which then induces an oscillation and subsequent upset attitude. crews need to remember: be aware of the causes and conditions that lead to aircraft upsets. It is important for pilots to understand the connected dynamic between aircraft airspeed, altitude, thrust, and G-loading. Being able to recognize what condition the aircraft is in relative to these variables will be vital in choosing the correct course of recovery. This is referred to as energy management. There are three basic kinds of energy during flight: kinetic energy, such as airspeed; potential energy, such as altitude; and chemical energy, or fuel, which transfers to thrust. The three different types of energy can be exchanged or traded for one another. For example, airspeed can be traded for altitude or vice versa. Kinetic energy, by its nature, needs to be continuously replenished by either potential or chemical energy. The process of trading different types of energy for each other is called energy management. During an upset condition, the energy levels will very likely be in a state of imbalance. In the example of an extremely nose-low attitude, potential energy, altitude, is rapidly being converted to kinetic energy, airspeed. In addition, if the engines are producing higher levels of thrust, chemical energy is adding to the levels of kinetic energy. Key elements of upset recovery include the following energy management steps: identify the energy state and trend of conversion, arrest the energy conversion, plan for the desired energy state balance, and execute a maneuver to achieve desired energy state balance. One factor of energy management that is worth remembering, especially for pilots of transport category aircraft, is that the process of producing a new energy state takes time. The amount of time to recover energy states is a function of applied forces and the mass of the aircraft. Therefore, aircraft with larger mass will take significantly longer to balance the energy states. Although stalls and aircraft upsets are unique from each other, they can be connected in some instances. Stalls can lead to aircraft upsets, and conversely, upsets can lead to stalls. It is important to remember that stalls are simply a function of angle of attack and can occur at any aircraft attitude or speeds. In the case of aircraft upsets that are accompanied with a stall, it is imperative that the crew first recover from the stall before the upset. Stall recovery techniques will be discussed further on in the lesson. Operation at high altitudes involves certain elements that may lead to aircraft upsets. For example, when the aircraft enters upper air currents of decreasing velocity wind shear, the backside of the power curve may be encountered. The pilot flying must increase thrust or decrease angle of attack to allow the aircraft to accelerate and resume normal climb or cruise airspeeds. This procedure may require sacrificing altitude in favor of airspeed to accelerate away from the backside of the power curve. Failure to accelerate from the backside of the power curve may result in a stall. In the event an aircraft upset or stall is encountered at high altitude, recovery can be more difficult than at lower altitudes. This is due to decreased control effectiveness from the lower density air at altitude. Crews should anticipate longer recovery times from upset conditions at higher altitudes. In the unlikely event that an aircraft upset is experienced, the crew must know and execute the proper procedures for exiting the condition. A number of factors exist, many of them psychological, that work against pilots successfully recovering from an upset condition. This topic will discuss these barriers, beginning with the startle factor. Because airplane upsets are statistically quite rare and by their nature unpredictable, there is associated with them a significant startle factor. This occurs when the flight crew is suddenly faced with a situation that does not match with their expected reality, leading to a strong sense of surprise. Crews may be startled by anything out of the ordinary, including, but not limited to, unexpected low airspeed, stall warnings, buffeting, or large changes in aircraft attitude. Startle factor is neither a cause for the upset nor an element of the recovery. It is a byproduct of the situation, which must be overcome before executing a successful recovery. Pilots can exhibit any of 4 possible negative responses to startle: early reaction, overreaction, indecision, or fixation. These responses are distinct from one another. During an upset, crews may experience any of them or none at all, depending on personality and the degree of the upset situation. Much like an automobile driver who is suddenly aware of slowly drifting into another lane, the startle factor can lead pilots to react quickly without analyzing what is happening. Crews who react too early without properly mentally engaging the issue are more likely to make an incorrect recovery action. In much the same way, pilots who respond negatively to startle are prone to overreact. This response, engaging in a proper corrective action but too aggressively or to an excessive degree, can very quickly exacerbate the problem. In some upset incidents, an overreaction led to a pilot-induced oscillation that might have been worse than if the crew hadn't reacted at all. Indecision can cause the pilot to become trapped in a mental cycle of obsessing over the negatives of possibly making an incorrect action. This stress over doing the wrong thing may lead the pilot to do nothing at all. Finally, in many instances, the startle factor causes the crew to fixate on one indication or data input. This creates a precipitous decline in cross-checking and situational awareness, wherein the cause of the upset might be missed. A loss of cross-check capability can be a strong hindrance to the recovery process. The best first step to combating the effects of startle is for crews to be aware of them. Pilots can begin by asking themselves, what would an upset look like, and how would it affect me emotionally and on a purely instinctual level? In addition, practicing situational awareness and resilience are the primary tools for overcoming the effects of startle. These tools will be discussed in an upcoming topic. Depending on the severity of the upset, recovery maneuvers may require either larger than normal G-forces or unloading the aircraft into the 0 or negative G regime. The psychological difficulty with this is that airline pilots normally make their best efforts at flying smoothly and keeping a constant positive 1G force. This is normal for providing a comfortable flight experience for the passengers and cabin crew. For an upset recovery, it is frequently not possible. Pilots must therefore be ready to overcome this inhibition and maneuver the aircraft into the 0G flight envelope. If 0G maneuvers are required, the crew will be faced with a flight deck environment that is both unfamiliar and which cannot be realistically trained for in a simulator. The inability to properly simulate a negative G effect will only amplify the startle factor experienced by flight crews during an actual aircraft upset. Be aware, the recovery process in a real airplane upset will feel and look very different than the training in a simulator. Pilots who are mentally prepared for a significantly different feeling, especially in regards to G-loading, will be more likely to overcome the effect and perform a successful recovery. 0G maneuvers can lead to any of the following: pilots floating against seatbelts and harnesses, or out of the seat if not buckled in, inability to reach rudder pedals due to floating, unsecured items flying around the flight deck causing obscured vision, and, depending on the aircraft and situation, possible transient caution alerts. Similar to pilots' reluctance to perform 0G maneuvers for recovery, most pilots rarely ever utilize the full control authority of the flight controls. This is something that is normally not done during routine line flying. However, due to the decreased control effectiveness of lower airspeeds, the crew should be prepared to use greater than normal inputs. Although full control input may be required during an upset recovery, the crew should beware against control reversals. There is no upset condition that would justify a rapid, full-scale control deflection from one side to the other. Pilots should understand that in some upset circumstances, the best recovery procedure may conflict with training for similar situations. For example, required training for crews includes recovery from an approach to a stall. The recovery from an actual aerodynamic stall, however, may require actions that are the opposite of approach to stall recoveries. Similar to negative learning for procedures, there are times when upset recovery can be negatively impacted by different aircraft experience. This is particularly true when system failures or aircraft idiosyncrasies are a factor in the upset. Pilots who transition into and out of aircraft with differing levels of automation are particularly susceptible to this type of negative learning. Flight crews should make themselves as familiar as possible with aircraft systems, paying particular attention to automation and degraded modes in fly-by-wire aircraft. Students should be aware that despite technological advancements in the field, limitations still exist with the FSTD's ability to recreate scenarios outside the normal flight envelope. It is important that upset prevention and recovery training is conducted within the applicable simulator's valid training envelope, or VTE. Excursions outside the VTE will not accurately reflect real-world aircraft performance and will therefore present a negative training experience. The upset prevention and recovery curriculum for all certified training programs is specifically designed to operate within the designated FSTD's valid training envelope. Most FSTDs may be used for a significant portion of training, up to full stall scenarios. Currently, the aerodynamic models of most FSTDs are unable to adequately represent the airplane in a post-stall regime. The updates to FSTD certification requirements and regulations are designed to extend the VTE to include full stall training and comprehensive upset prevention and recovery training. For more information regarding your training device's specific VTE, capabilities, and limitations, contact your instructor or training department. It should be noted that the simulator performance during upset recovery training is dependent on certain variables, such as weight, CG, atmospheric conditions, aircraft altitude and airspeed, etc. Actual upset events are unlikely to take place at the exact configuration, altitude, and speed as trained in the simulator. Pilots should be aware of these negative learning aspects and be prepared to incorporate their knowledge into actual recovery techniques. This topic will discuss the most effective techniques of safely exiting an aircraft upset if one should occur. While the specific actions and techniques for different kinds of upsets will vary, the following 3 activities should be part of every recovery. Manage the energy, arrest the flight path divergence, and recover to a stabilized flight path. While situational awareness is an important tool for avoiding aircraft upsets, it can also be equally important in recovering from one. Recognizing and understanding the upset scenario is crucial for a successful recovery. Pilots who are engaged and actively monitoring the aircraft will be much more situationally aware and less susceptible to startle effects. Crews should avoid reacting when feeling startled into fixating on a single indication. The first step is to regain situational awareness and analyze what is happening before acting. Next, purposeful communication between crew members will ensure both pilots have all the knowledge regarding the aircraft's condition and are working together towards a common solution. At the first indication of a flight path divergence, both pilots should announce what is being observed. Proper communication will greatly increase the level of crew situational awareness. This is the first building block for the 3 steps of upset recovery: recognize, recover, and rebuild. An important personal quality for combating the startle effect is resilience. Resilience is our ability to adapt and bounce back when things do not go as planned. Resilient people are described as having the following attributes: view difficulty as a challenge, have clear, solid goals, as well as a desire and commitment to succeed in those goals, focus on things they have control over, have a positive image of the future, and are empathetic and compassionate, but do not bow to peer pressure. Some people are naturally resilient. Others need to work at it for it to be an effective piloting tool. Those people who are not naturally resilient can use the following techniques to develop and hone a sense of resiliency. Get enough sleep and exercise. Practice positive thinking. Practice cognitive restructuring to change the way you think about negative situations. Learn from your mistakes. Choose to respond to negative events in positive ways. Maintain perspective. Set smart, effective goals. Build your self-confidence. Practice developing strong relationships with your peers and colleagues. And focus on being flexible during unplanned events. Practicing resiliency fosters a personality of confident, informed decision-making skills, as well as the ability to confront and overcome setbacks. Many upset recovery procedures and techniques may use the phrase, "unload the aircraft." Most commonly associated with nose-low upsets, unloading the aircraft means to decrease pitch inputs to minimize the G-load factor being applied to the wings. There are two reasons to do this: increase roll effectiveness and avoid accelerated stalls. As G-loading increases, which commonly occurs during an upset, aileron effectiveness decreases. Unloading allows a faster roll rate and therefore a faster recovery. Additionally, as airplane bank increases, so does the stall speed. In a high bank upset, the aerodynamics of the wing will cause the stall speed to increase dramatically. If a pitch-up maneuver is executed during these high bank conditions, the low-speed buffet regime will increase and an accelerated stall may occur. Unloading the wings and keeping the aircraft at or below 1 G will prevent this stall from occurring. The first few moments of an airplane upset recovery are vital to ensuring a safe outcome. The flight crew must first resist the reflex to initiate large, exaggerated control inputs. These excessive movements can easily exacerbate the upset or lead to a different upset situation. Gentle and timely inputs up to full control authority should be used. For many pilots, the first instinct during an upset is to attempt to troubleshoot the cause of the upset. This can delay the recovery process and possibly allow the upset to worsen. Therefore, troubleshooting the upset cause should always be secondary to the recovery process. The only exception to this rule is in some cases of flight control malfunctions. In these instances, it is possible that the malfunction would preclude a safe recovery maneuver. The crew must use its best judgment when deciding the safest course of action. Due to the unusual aircraft attitudes experienced during upsets, outside visual references are often not reliable sources of attitude information. Many times it can be difficult or impossible to see the horizon. Therefore, it is necessary for the crew to use the primary flight instruments when analyzing aircraft attitude. Additionally, because thrust is an important factor in the recovery, the engine instruments should be included in the instrument scan. If for any reason instrumentation or system failure is suspected as an upset cause, the pilot flying should include either the other pilot's instruments or the standby instruments in their scan. Autopilot and auto throttles are intended for use during normal flight conditions. If the autopilot and/or auto throttles are engaged during an upset, the flight crew must quickly recognize and evaluate the actions of the automation. In the event of an upset where the autoflight systems are responding appropriately to recover, the correct course of action may be to leave them engaged. Some training studies have shown that an autoflight system, if engaged and operating properly, can recover in a safer manner than the flight crew. However, if an element of the autoflight system is not responding correctly, it must be disconnected. For the purposes of this lesson, the following upset recovery maneuvers will assume the autoflight systems are not responding properly and should be disconnected. Crews should always remember that the recovery for a full stall will usually differ from recovering from an approach to stall. A stall is an out-of-control condition that can exhibit any of the following characteristics: buffeting, which could be heavy, lack of pitch authority, lack of roll control, or inability to arrest descent rate. The primary goal of a stall recovery is to reduce the angle of attack and return the wing to a state of producing lift. In almost every flight regime, especially high altitudes due to the lack of excess available thrust, this means sacrificing altitude to achieve the required angle of attack. Therefore, recovering from a stall is initiated by applying a significant nose-down pitch input. This may be very counterintuitive, since the aircraft may already be in a nose-down pitch attitude with altitude likely decreasing. This nose-down pitch should be maintained until the stall recovers. In some situations, it may be necessary to reduce thrust to prevent the angle of attack from increasing. This is due to a combination of reduced elevator effectiveness and the upward pitch moment caused by underwing-mounted engines. In many instances, the stall recovery will result in or cause the aircraft to remain in an upset condition. Always recover from a stall before initiating an upset recovery. Normally, nose-high upsets are indicated by airspeed decreasing, altitude increasing, and VSI indicating a climb. In an upset with pitch more than 25 degrees nose up and wings level, execute a recovery by doing the following. Disengage autopilot and autothrottle if required. Recognize and confirm the situation. Apply nose-down elevator. And if required, use trim to assist in achieving a decrease in pitch. Use of elevator trim should be done with caution. Avoid using too much and stop trimming as soon as the required elevator force lessens. Excessive pitch trim or rudder may upset the situation or result in high structural loads. If these steps are taken and the pitch is not under control, the pilot flying may take additional steps. First, the crew can decrease engine thrust to induce a lower pitch moment. This is only advisable with underwing-mounted engines and only if enough altitude permits. The second option is to roll the aircraft to initiate a nose-down pitch movement. This transfers some of the wing's lift into the horizontal vector and should allow the nose to fall. While full aileron authority may be used, angle of bank should not exceed 60 degrees during this maneuver. In the event roll control is ineffective, the crew may use rudder input to initiate a roll. However, only a small amount of rudder should be applied. Use of too much or too quick of an input may lead to a loss of lateral directional control. Nose-low upsets are usually indicated by airspeed increasing, altitude decreasing, and VSI indicating a descent. Recovery from a nose-low condition will depend on whether the aircraft is in a stall or not. The recommended nose-low recovery is to do the following. Disengage autopilot and autothrottle if required. If in a stall, recover by applying nose-down elevator. Roll in the shortest direction to wings level if in a bank. Adjust thrust and drag if required. And recover to level flight, using pitch trim to assist with control forces if desired. The recovery is complete when aircraft pitch, thrust, and configuration match the desired airspeed. During the pitch-up recovery maneuver, the pilot flying should take care not to pitch up too rapidly. An abrupt pitch maneuver can cause either an accelerated stall or a high G-load that exceeds the structural limits of the aircraft. In a high-bank, nose-low upset, altitude is rapidly being exchanged for airspeed. For this reason, it is important to reduce G-loading when attempting to roll wings level. The roll procedure should be as follows. Unload the airplane by decreasing back pressure. Use full aileron and spoiler input to recover the roll rate to the nearest horizon. And add rudder input if aileron is ineffective at correcting roll. Keep in mind that the first step, unloading the airplane by pushing forward on the control wheel, will be counterintuitive. This step, however, will be important to ensure adequate aileron effectiveness and roll rate. It is also important to remember that only a small amount of rudder should be used, if at all. Rapid or sustained rudder pedal inputs may result in loss of directional control and/or structural damage. In transport category aircraft, it is not recommended to roll through the horizon in an attempt to achieve wings level more quickly. Roll recovery should always be in the shortest direction to wings level. This concludes the upset recovery lesson.